This conference will now be recorded.
Very good evening, students. Today we are continuing with the discussion of various questions from previous year's JEE papers on the topic wave optics. So we have few questions to discuss today. Let us start our discussions. So this question says, in Young's double slit experiment, intensity at a point is 1/4 of the maximum intensity. 1/4 of the maximum intensity. So what is the angular position of the point? Look, see, Young's double slit scenario is something like this. There are two slits. Slits are separated by distance small d, and this is the separation between the plane of the slits and the screen, that is denoted by capital D. And look, this angle, if this angle is theta, this must be also theta. So if I say that the particular point where the intensity is becoming 1/4 of the maximum intensity, so let us say this is that point where the intensity is becoming, or intensity is 1/4 of the maximum. Okay, so what is the angular position of this particular point? That is theta over here. So if we know somehow this distance, okay, this distance, then we can find out easily. Okay, how do we find out? This is d, so tan theta will be equal to x by d, but we have to see what are the informations given over here. So intensities, sorry, information is only intensity. We don't have this x, we don't know what is this x, so better to go with some other way. Okay, see, in Young's double slit experiment, intensity intensity at any point on the screen, any point on the screen can be given by I is equal to I max, maximum intensity, into the cosine square of phi by 2. Okay, so this is the formula for getting intensity at any point on the screen. Okay, now look here, my intensity at this point P is 1/4 of I max, and that is equal to this. We can write cos square phi by 2. Okay, so I max goes, so we get cos phi by 2 plus minus 1 over 2. So for the time being, let us take with positive modulus of this. So look, cos theta or cos phi by 2 will be half only when phi by 2 is pi over 3. That means 60 degree. So what we get as phi? phi is 2 pi by 3. What is this we got? This is the phase difference between the rays S1 and S2. So this is the phase difference. Okay. So what we have got here? We have got phi. Okay. So with this, what we have got? We have got the phase difference. Therefore, the phase difference between the interfering wave at P, difference between the rays at P is phi is equal to 2 pi by 3. Now see, for interference, okay, let us first find out what is the path difference. We know path difference delta x will be, okay, in fact the phase difference del phi is given by 2 pi by lambda into path difference, that is delta x. So if you want to find out what is path difference, then delta x is equal to lambda by 2 pi, lambda by 2 pi into delta phi, that is path difference, sorry, phase difference. So lambda by 2 pi and phase difference is 2 pi by 3. Okay, so what we have got? We have got path difference to be equal to lambda by 3, and we know for interference d sin theta is equal to path difference. Okay, path difference has to be equal to the d sin theta. Okay, so this is equal to dx. So from here sin theta will be equal to dx by small d, and theta will be sine inverse. So dx is lambda by 3, so sine inverse lambda by 3d. Okay, so from here the option 3 will be the correct answer. Okay, so this is how what we have done. Actually we have found out the path difference, and that we have written is equal to, actually this is the path difference and this is in terms of angular position. Okay, so in terms of that we have obtained d sin theta. So these two are equal actually. From here if you find out the path difference between these two will be d sin theta only, and that is equal to dx. Okay, so dx, so from the figure we get the path difference between these two guys will be, these two interfering rays at P will be d sin theta, and that is equal to the dx what we have got is lambda by 3, and from there we can find out the angular position. So this is how you can solve this problem. Okay, all right, let us go to the next problem. This is also a very interesting problem. Before I solve this problem, let me give you the options here. Options I have not put here. So the options are given as A is equal to 1.2 centimeter. Option B says 1. Okay, 1.2 millimeter. Option C is 2.4 centimeter, and option D is 2.4 millimeter. Let us now read the question. The question is that a beam of light of wavelength. So lambda is given 600 nanometer. Wavelength 600 nanometer from a distant source. Distant source means you have got plane wave front. Okay, that means front of a diffraction. Okay, here it is happening. Source falls on a slit one of on a single slit. Sorry, on a single slit of 1 millimeter wide. That means A is equal to 1 millimeter. Okay, and resulting a diffraction pattern is observed on a screen 2 meter away. That means the capital D also is given 2 meter away. So these are the parameters given. Now you have to find out what is the distance between first dark fringes on either side of the central fringe. So look, one thing here, a beam of wavelength 600 nanometer from a distant source falls on a single slit of 1 millimeter wide. A resulting diffraction pattern is observed on a screen 2 meter away. The distance between the first dark fringes on either side of the central bright fringe. So first dark fringe, see, this is the typical diffraction pattern in the single slit diffraction experiment. You can see this is the central maxima, and consecutively you will get this is first minima, this is also first minima, this is first maxima, after that this is another maxima. So these are actually symmetrically situated from the center or from the central fringe. Okay, so central bright fringe, see the width of the central bright fringe itself is giving you the distance between this two first. This is also minima, so I can write this is minima, first minima on one side, minimum, and this is another side, this is first minimum, first order minimum, minima or minimum. Okay, minima, let's write minima. Okay, so you look, the width of the central fringe, width of the central fringe will give you the distance between. So this width actually the linear width. So here question is the distance between the first dark. So I can write that it is clear, it is clear from the diffraction pattern that the linear width of the central bright fringe is equal to the distance between first dark fringes on either side, fringes on either side of the central bright fringe, CB, if I'm writing central bright fringe as the question is given here. So I have found out that it is the linear distance, a linear width of the central maxima. That itself will give you the distance between the first minima, okay, on either side of the central fringe. Now look, what is the angular separation here? Angular width is, so angular width of the angular width, so this is actually theta. If you look, dth, width of the central fringe is 2 theta, which is here. See, we know for diffraction pattern, we know d sine theta is equal to lambda. This is the first dark fringe. So this is, if theta is very, very small, so we can write d theta, nearly d theta is equal to lambda. So from here we can find out theta is equal to lambda by d, and that's how this will occur in the other side. So you look here, the angular separation, so this angular positions angular position minus lambda by d and plus lambda by d. So what is the, so these are theta actually, theta. So what is the 2 theta? Then 2 lambda by d. So this is the angular angular width. So now look here, we have got angular width 2 theta. This is 2 theta, we have got already, and this is the beta, which is the linear width, width of the central fringe, okay, width of the central fringe. Now if this is d, how do you get, see, this is a linear, we know the arc will be equal to angle by d. I'm sorry, this is just opposite to that. So angle is 2 theta, that is theta is equal to s by r, we say, right? So beta 0 by d. Okay, so what is beta 0 then? Then 2 d and theta. We have got 2 d is all right, and theta we have got lambda by d. Okay, so we have got d lambda by d and along with a 2 factor. Okay, so this is the one. I think this, I should not write d, I should write, we are a little bit habituated to write d, we will be writing here a. So here also it will be a, not the d. This is d, it is written, this is just a, what we said, slit with a and d are same here. Okay, that's why we have written anyway. So we have got the linear width as 2 capital D lambda by given a. So 2 is all right, and this d also 2 meter, lambda is given 600 nanometer, and this has been given, I think, 1 millimeter, 1 millimeter slit width. So 1 millimeter is 10 to the power minus 3. Look then, this 4 into 6, so we can directly just do the calculation part. So 24 into 10 to the power minus 4, because here this goes 3, this is 10 to the power, so it will be actually, this is in meter anyway. So you look, 10 to the power minus 3 meter, so it is 2.4 millimeter. Okay, so here there are options. So 2.4 millimeter will be the correct answer for this question. So I hope it is clear to you. Now we'll go to the next question. So this is from polarization. In fact, we'll take a few more questions from polarization. And this is no, I don't think this is actually IIT JEE in 1994, I guess. This is the problem from 80. Okay, this is a bit old problem, but this is very popular and very easy also. This is old problem. Anyway, let us see what is this problem. This is the problem which generally will be there in NEET or JEE mains exam, etc. So, what is this question saying? A ray of light from denser medium strikes a rare medium. So this is denser medium, this is rarer medium. You can think of water to air, okay? Water to air, okay? So strike a denser medium, sorry. A ray of light from denser medium strikes a rarer medium at an angle I, as you see here. At an angle I at the interface. See, this is I. The reflected ray and refracted ray, they make an angle 90 degree. The reflected and refracted rays make an angle 90 degree with each other. So these are the two. So this is reflected ray, and this is refracted ray. They makes an angle 90 degree. Since this is actually, see, you can see this is actually 180 degree total. It is 180 degree, and also this is 90 degree. Here it is given r plus r prime is 90 degree. Okay, the angle, see, the angle of refraction, angle of reflection are given as r and r prime. These two guys, they make an angle 90 degree. This is actually 90 degree. Okay, if this is the 90 degree, okay, so if this is 90 degree, then these two guys also have to be 90 degree, because ultimately, see, this the total angle will be 180 degree. This total will be 180 degree. So this is 90 degree, means this plus this also will be, this should be 90 degree. So this is the thing. Now if we apply, so let us see what are the options. The question is, the critical angle is given by sine inverse tan r, or sine inverse tan I. So this is a very standard question. You can even remember the result also, so that you can just fill in the answer like in the OMR sheet. I have seen this question is very common for NEET exam. Every year, some or the other way, this question will be given. Okay, so not every year, most of the time it is given. So look here, we have got this relation, so I can write this r prime is the refraction, angle of refraction. So this is this. See, applying Snell's law, what we will get, because this is refraction, I'm just considering the reflection, sorry, refraction. Applying Snell's what we would be getting. So we can write n1, okay, n1. That means the refractive index of this denser medium is n1, and rarer medium is n2, suppose. So n1 sine, I'm writing this is denser and this is rarer, nd by, so N1 sine I, nd sine I is equal to nr sine r prime. This is the angle of refraction, that's why. So now if we put the value of r prime, so what we get, nr sine of 90 degree minus r. So this would give you nr cos of r. Okay, and here it is, this is sine I. Okay, now look, if I just okay, let us use this portion itself. So we have got nd, or let us say nr by nd is equal to sine I by sine I by cos of r. See, cos of r, and see, I and r always will be equal. Okay, I and r will be always equal, so I can equivalently write this as cos I. Okay, if I require, I can write it. Okay, so you can see that nr by nd is equal to tan of I. Okay, I hope you have got this. Now what we know is that for critical angle, what we know, for critical angle IC, we know that this nr by nd, this will be, because you know, if it is critical angle, because let me just tell you. So here, if this is unpolarized light, both perpendicular and parallel components are there. So when this condition is occur, like has been seen, that re reflected ray and refracted ray, they are making a 90-degree angle at that particular angle of incidence, that is called critical angle of incidence, where in the reflected ray there will be only the perpendicular part. Okay, the light wave light with electric field vector oscillating in the perpendicular direction, and this the electric field, the light with electric field oscillating in the plane will be transmitted. Okay, so if I just consider kind of total internal reflection, so we know that n2 by n1, or this is rarer by denser, is equal to sine critical angle. Okay, sine IC, this we know, sine IC. So if we put this as sine IC now, sine IC, because we are treating this as critical angle of incidence where this particular thing happens, and this is similar to the total internal reflection if you see in the geometrical optics part, so, or ray optics part. So sine IC is equal to tan I. Sine IC is equal to tan I. Okay, sine IC is equal to tan I. Okay, so since we have got this thing, I think we should write this as R, and let us put this also as R. Okay, then it will be tan R. Okay, if we want to do in that way, then IC will be sine inverse tan of r. So this will be the answer. Okay. All right. So the answer will be, see, IC is equal to the critical angle of incidence is sine inverse tan of r. So this will be the answer. I don't know the, like, since I and I are the same, I don't know what is the use of giving this option as well. Okay, sine inverse tan, I don't know whether I have written it wrongly, but this seems to be the same actually. Sine inverse tan r, yes, there are two options, sine inverse tan I. This two seems the same because I can be equivalently written as r. So if this I and I are equal, so these two options are same actually. Okay, I don't know why this has happened. Anyway, so this is fine with okay, so we have understood this. Now we'll just pick up another good problem. This is from JEE advanced paper. This is very interesting problem. We'll first read the problem and let me just uh, okay, let us first read the problem, then we'll go for the options and see what happens here. See, the question says two coherent monochromatic point sources S1 and S2, as you see here, S1 and S2 of wavelength. So they are producing wavelength, a light of wavelength, or sending light of wavelength 600 nanometer, and they are placed diametrically on either side of the center of the circle as shown in the figure. So this is the circle, and you see in one of the diameter, on one of the diameter S1 and S2, so horizontal diameter, so S1 and S2, they are symmetrically placed. That means this distance are same. Okay, symmetrically placed. Okay, so the thing is that the sources are separated by a distance. So this small d is given here. Small d is 1.8 millimeter. The arrangement produces interference fringes visible as alternate bright and dark spots on the circumference of the circle. Okay, so interference pattern, how do you see interference pattern? The interference pattern will be spot pattern, and those will be situated on the circumference of the circle. Now, angular separation between two consecutive bright spot, angular separation is delta theta. The angular separation between two consecutive bright spot is delta theta, that is given here. Which of the following options is or are correct? So first option is, so let me first write the option section. The first option says the total number of fringes produced between total number of fringes produced, total number of fringes produced between P1 and P2 in the first quadrant, first quadrant, that means this one, you see this P1 and P2. So the total number of fringes produced between P1 and P2 in the first quadrant is close to 3000. Okay, close to 3000. Okay, first of all, let us try to see whether this option itself is correct or wrong. Let us first see this thing. We'll just write one by one options and try to give reasons whether that is wrong or right. So you can see that rays will be, see, one ray will go from here, okay, then another ray will reach. So suppose this is a point P where the interference pattern is forming, okay, spot pattern like this is forming here, okay. One ray is this one, another ray is this one, meeting here and producing spot pattern. All right, so you see this angle is theta, this angle is theta, sorry, delta theta. If we say okay, let us just do one thing. Let us consider the angle theta between these two lines, okay, theta, which is actually increasing in this way, increasing in this way. So the now theta is angle between P, so this is O center, P1 OP, in between them the angle is theta, okay. And this actually this is delta theta given, the angular separation between these 2 points, okay. If I say this is Q, okay, so actually P O Q, that is angle delta theta. And now what we have considered is P1 O, that angle is theta, okay. So we see theta is measured from the vertical, this vertical, assuming that the circle of the circle to be the large, to be of large radius, okay, and the path difference between these 2 points, path difference between these two, what will be the path difference? Delta x is equal to s1 p, you can see that s1 p minus, or let us take difference s2 p, let us take this as difference. So this we can find out in terms of angular uh, this thing. See, we know path difference is equal to d sine theta, right? D sine theta, we know that, okay. So here d is given, fine. So what is the path difference between these 2 points? We can find out. Actually, see, the angle theta is 0 at P1, because the angle I have taken theta from P1 to P2, okay. Angle is increasing from P1 to P2, and the angle theta is 90 degree, this is 0, the 90 degree at P2, right? Then what is the path difference? Path difference is nothing but d alone, okay. Path difference is d alone, okay. Path difference is d alone, okay. So delta x will be d alone, because theta at this point is 0, so so this is 0, and at here this is, so if suppose the fringe is, this is the maximum order, right? This is the maximum within this quadrant, okay, maximum in this quadrant, okay. So I'm just finding out the two rays or the path difference between the P1 and P2. Okay, so path difference between P1 and P2 I have found out. So I have got delta x is equal to D. Okay, now one thing you can just see from this figure that from the see, if you just remember Young's double slit experiment, we know that see, d theta is equal to lambda, right? So from here I can find out what is d. D, uh, I'm sorry, I can find out, yes, that I can find out. So what will be d by lambda? What is d by lambda? Let us say d by lambda. D by lambda is 600 nanometer. I'm sorry, 1 point this 1.8 millimeter by lambda. Lambda is 600 nanometer. So if you just make with proper unit, so what you get, minus 3, this will be 600 into 10 to the power minus 9. Look, this is 18 10 to the power minus 3, 10 to the power plus 9, and 10 to the power minus plus, sorry, minus 2 divided by 6. So this will be 3, and it will be, you look, it will be actually one more will come here, so 10 to the power minus 3 here. So you'll see, you'll get here 3000. Okay, 3000. So d by lambda is equal to 3000. Okay, then what will be d is equal to, d is equal to 3000 into lambda. Okay, 3000 into lambda. So if we get that, then between P1 and P2, how many fringes are occurring? How many fringes will be occurring between P1 and P2? Because see, the extreme, this 2 has path difference this, path difference d. You look here, d is equal to n lambda. Okay, we have got already d sine theta is equal to n lambda, or d is equal to, so sine theta is 90 degree, so that's why I'm writing d is equal to n lambda. So from here we can find out what is n, because d is already found out. D is equal to the path difference anyway, so d is equal to n lambda. Okay, so what is n? 3000. Okay, nearly equal to 3000. So this path difference will be, path difference, this is d, and that is equal to n lambda. Okay, we know for interference, so d sine theta is equal to n lambda. Okay, integral multiple of lambda. Okay, so here this theta is 90 degree at this particular point, so we take d is equal to n lambda. So d is nothing but the path difference between these two, okay, these two extreme points. So the total path difference I have got, that means total number of order, total order we will be able to get. Okay, the maximum order we will be able to get here. The maximum order of the fringe will be obtained at this P2. Okay, maximum order will be obtaining here at P2. And what is that order? That is a 3000. That means how many? So here, starting from here, so there will be 3000 fringes occurring in this first quadrant. Okay, so the first option was 3000, close to 3000 is fine. Okay, there will be close to 3000 fringes in between this. Okay, now second option will see what is the option B. Second option, that is a dark spot will be formed at the point P. A dark spot will be formed at P2. This is wrong because we have already considered this synthesis is called N lambda to be here, happening here. So that is the condition for the bright fringe. So that's why dark spot will not occur over here. And option C is at P2 order of the fringe will be maximum. That is also true. At P2 the order of the fringe will be maximum. Fringe will be maximum. Okay, I'll just go to the previous. See, we have seen the path difference. Path difference will be D. That is the maximum, and we have shown that D is equal to sine theta n lambda. So there are maximum order 3000 order fringe. So this will be actually 3000 order. Okay, that is the maximum order of the fringe at P2. So this is also correct then. Okay, then next, what is the fourth option? The fourth option says the angular separation between two consecutive bright spot decreases. Angular separation. See, we know that D is equal to, okay, let me just write the option first. The angular separation between two consecutive bright spots decreases as we move from P1 to P2 along the first quadrant. Along the first quadrant. See, we have taken that angle is increasing in this way, theta. We know path difference, or let's see, D is equal to, we know that the path difference dx is equal to D sine theta. Okay, D sine theta is equal to n lambda, we have said. This is the angular path difference. So from here actually we will be able to find out some relationship. See, this is also equal to for the bright fringe to occur, what will be happening? Here it is n lambda. Okay. Now, if we just differentiate this part alone, see D of D, I'm sorry. if I just take the differentiation, d anyway constant, this will be cos theta and d theta, and here in dn into lambda. Okay, this is dn into lambda. So d theta by dn will be lambda by d of cos of theta. Okay, this is the angular separation between consecutive fringes. Okay, so if you look this is a constant term, this is constant term, only varying is, so d theta dn is inversely proportional to cos theta. Now look, theta, see cos theta value of the cos theta is, cos of theta is maximum at p1, and as go down and down, cos theta value of the cos theta is decreasing, right? It is going towards 0. So here cos theta value is 0. So maximum here and minimum here. That means as you go, this particular quantity, see if this is becoming lesser and lesser, then this will be actually, this as a whole, this fraction will be increasing. That means d theta by dn, that is the excuse me angular separation or angular distance, increases as angle theta increases, right? Increases. That is the thing. So here what was there? The angular separation between the consecutive bright spots decreases as move from P1 to P2. So P1 to P2, you are moving P1 to P2 means you are increasing theta. If you increase the theta, angle theta, then this dn by d theta by dn, that means the angular separation between two consecutive fringes will actually increase, not decrease. So this is also not correct. So A and C options are correct for this question. With this, I think we'll stop it here for today. Next day, we'll directly take up problems from polarization, because from polarization part there may be many other questions, many other types of questions. We'll pick up those, and then we'll move on to the ray optics part. Okay, so next class we'll complete the wave optics part. So thank you for your patience. Bye for today.